Okay, now we want to explore doing limits algebraically, and we're going to also start to build an intuition for what limits are and how to look at them without doing a lot of work, such as using a calculator or technology to plug in numbers really close to what we're approaching, or without having to graph the function and then use the graph to tell the limit. So what we're going to focus on for this video are algebraic limits. With regard to piecewise defined functions. Okay? And so we're gonna start with an example and do some analysis. So let's suppose we have this piecewise defined function. Let's suppose that this function f of x equals this three-piece function, where the first output is x minus 1, and that's our output if x is less than or equal to negative 1. And then let's say the second output is the constant negative 2, and that is true if x is between negative 1 and positive 1. And let's say the third output is the quadratic function x squared plus 5 if x is bigger than positive 1. Okay? So there's our function. What we're going to do with this is evaluate various limits. Okay? So let's start with maybe something like this. Let's determine the limit as x approaches, how about 4 of f of x. Determine the limit as x approaches 4 of f of x. Well, so when we look at this function, we're looking at x values that are really close to 4. And so whenever x is really close to 4, 3 point something, 4 point something, right, that neighborhood around 4, we're talking about x values that are definitely bigger than 1. So when we're looking at this limit, we're really only concerned with this part of the piecewise defined function, this x squared plus 5 portion. So in this case, we can say that the limit as x approaches 4 of f of x equals the limit as x approaches 4 of this piece of the function x squared plus 5, because whenever x is near 4, it certainly is greater than 1. So we use this output. Now, this is a very predictable type of function. This is just a standard quadratic function. It's a parabola if you were to graph it. And so hopefully you can see that without plugging numbers in for x, right? If you look at numbers close to 4 for x and you square them, you're going to get numbers close to 16. In fact, as x gets infinitely close to 4, x squared gets infinitely close to 16. And so this limit turns into just 16 plus 5. You just literally directly substitute 4 in for x, and you see that you get 21 for your limit. Okay? So we didn't have to actually get out the calculator and plug in numbers to see this. Intuitively, it makes sense that as x gets close to 4, this guy gets close to 21. Now the key is, the reason we could do this is because we know that whenever x is near 4 from the left or the right, it uses the same output formula. Okay, so this example is not very interesting as far as that goes, but it gives us this idea of how to evaluate limits intuitively. So let's look at a more interesting limit. And so the x values of interest here for this particular function, where unique types of things happen, are from the first output formula to the second output formula. That change happens whenever x is negative 1, right? If x is less than or equal to negative 1, we have this output, but if x is bigger than negative 1, we have this output. So negative 1 is an x value of interest. Positive 1 is also an x value of interest because that's also another x value where the output shifts from one to another. Okay, so let's start with, let's look at the limit as x approaches negative 1 of f of x. So determine the limit as x approaches negative 1 of f of x. Now, contrary to the prior example, On one side of -1, in fact, to the left of -1, this is the output of the f function. To the right of -1, immediately to the right of -1, this is the output of the f function. So to evaluate this two-sided limit, we have to look at both one-sided limits independently. So let's get started on that. Let's look at the limit as x approaches -1 from the left of f of x, of the big piecewise defined function. Well, when we're looking at x values to the left of -1, so if here's -1 on the number line, maybe -1.1 or -1.01, right? Those x values are right here, less than or equal to -1. So that means the limit of f of x is going to be the same thing as the limit of the x minus 1 function, which we write like this. Make sure you write your limit on every step as you evaluate until you actually take the limit of the expression. And now, because this is a very predictable function, nothing weird happens at -1, we can just directly substitute -1 in for x. And notice I'm not writing my limit now because I'm applying the limit to this function to get -1 minus 1, which is -2. So the left-sided limit of this piecewise defined function at -1 is -2. Now let's look at to the right of -1. So the limit as x approaches -1 from the right of f of x. And for this piecewise function, when we're looking at x values slightly to the right of -1, we're talking about x values bigger than -1. We're talking about this output formula. So this is the same thing as the limit as x approaches -1 from the right of the constant output -2. Now, this is a little strange, maybe the first time you see it, but this output is constant, no matter what x is. Because there's no x in the formula, it does not have an impact on what the output is. So this limit is just -2. All right? So now we know both one-sided limits. The left-sided limit results in -2. The right-sided limit results in -2. So the conclusion is, so the limit as x approaches -1 from both sides, as we approach from both sides, the y value approaches -2. So the limit as x approaches -1 from both sides is -2. Okay? Now, if these happened to be different outputs, different limits, then the two-sided limit wouldn't exist because they wouldn't meet up at the same value. Okay? So the two-sided limit at -1 is -2. So let's look at the other x value of interest in this case, which is when x is +1. And you could pause the video and try to do this yourself. You should have all the tools you need now. Let's approach 1. Determine the limit as x approaches 1 of f of x. And again, because to the left of x equals 1, this is our output, and to the right of x equals 1, this is our output, we have to look at both one-sided limits. So let's look at the limit as x approaches 1 from the left of f of x. As x approaches 1 from the left, we're talking about x values less than or equal to 1, so we use the output formula -2. So this is the same thing as the limit as x approaches 1 from the left of the constant function -2. And as we said before, regardless of the value of x, -2 is always the constant -2. Okay, so the left-sided limit here is -2. Now, make sure you understand, x is approaching +1 from the left. This does not mean -1. We're approaching +1 from the left. So it is a different limit than we looked at before. Now, let's look at the limit as x approaches +1 from the right of f of x. Now we're looking at x values slightly bigger than 1, so we're talking about x values greater than 1. So we use the third output formula. So this is the same thing as the limit as x approaches 1 from the right of the expression x squared plus 5. And because nothing strange happens with this function near 1, we can just plug 1 in. 1 squared plus 5 is 6. Okay? And so now what we see is that the left-sided limit's -2 at 1. The right-sided limit at 1 is 6. So the limit as x approaches 1 from both sides of f of x, well, what it looks like is as we approach from the left, we're coming down here to -2, and as we approach from the right, we're coming up here to 6. They don't meet up, so the two-sided limit does not exist. And so there are a few examples of finding limits of piecewise defined functions, looking at the x values that aren't that interesting, looking at some x values that are interesting, applying left and right-sided limits, and then making conclusions about the two-sided limit.